Hello guys, welcome on Tesla Adventures. In this video we are going to discuss the excess pressure inside a soap bubble and a water droplet. So you must have heard about the excess pressure, and you should know that the pressure inside the soap bubble is actually greater than the pressure outside the soap bubble, or the pressure inside a water drop is greater as compared to the pressure outside it. Now this is obviously it is due to the surface tension. So we can see the scenario that there is a bubble, and this bubble is actually having air inside it, and air is also outside this bubble. So the outer air is pushing this bubble inwards with a pressure of P naught, and the inner air is pushing this bubble outwards with a pressure of P naught plus P axis. Now we can easily understand that P naught is counterbalanced by this P naught, but what about P axis? So we know that obviously a molecule, if you talk about a molecule which is situated on the surface of this liquid film, this molecule is experiencing some cohesive force acting on it by the neighboring molecules, and due to this force there is a net force which is acting towards the center of this bubble. So this net force which is acting towards the center of the bubble is due to the this surface tension force, and this force is needed to be balanced, and to balance this unbalanced force excess pressure is required inside the bubble. So the pressure inside the bubble is greater than the outer pressure to counterbalance this net cohesive force. So now let us also see that what is the value of this excess pressure. So to find out the value of this excess pressure, let us imagine a soap bubble which is a half soap bubble. We are just imagining this half soap bubble. Actually it is a complete bubble, and we cannot subdivide a soap bubble into two equal halves. So we are just imagining this soap bubble as hemisphere, and obviously we can say that this hemisphere is being pulled by the lower hemisphere by this cohesive force which is acting on the this circle which is on the diameter of which is on the base of this hemisphere. So the molecules of the liquid which are situated on this circumference of the base are being pulled in the downward direction by the cohesive force applied by the molecules which are on the circumference of this base. So these molecules are pulling each other towards each other, and obviously this hemisphere is having a net cohesive force acting in the downward direction. To counterbalance this cohesive force, excess pressure applies a net force in the upward direction. You can see that pressure always acts perpendicularly to the surface of the sphere. But obviously, as we can say that this component, if this is the force acting due to excess pressure, so this component of the force and this component of the force will be cancelled out, and these components will be added up, dFy. This is dFy. So what we can say that if this area is ds, so we can say that this is ds, and this is the dF force which is force due to excess pressure. This angle is theta and this is this area is dA, and this is dx, and this area is dy. So if we see that, first of all let us erase this. So this is dy. So the projection of dA along this plane is dy, and the projection along x is dx. Now we know that the force dF will be excess pressure P axis into area dA, and the y component of this force. So if we see that the force will be acting like this, if this is the area, force will be acting like this, and if this angle is theta, this is theta. So this is also theta. So the y component of the force is dF cos theta. Now dF is axis pressure into area, and dF is p axis into area. Now obviously if we need to find out dFy, so dFy will be dF cos theta. So dFy will be equal to p external into dA cos theta, and dA cos theta is dx. So we can say that dFy is pxs into dy. In fact, this is dx. This is the force component of y direction. So now to find out the net force in y direction, we must integrate it. So this is integration of dF into y. So Fy will be equal to integration of p axis into dx. Actually dx is not the length, dx is x component of the area. So we can say that this Fy will be equal to p axis into dx. Now integration of dx is the total area projection of x plane, this the area of projection in x axis. So you can see that the projection area of this hemisphere along the base will be area of the disk, which is pi r square. So Fy will be equal to p axis into pi r square, and this is balanced by the cohesive force, which will be surface tension will be 2T. See, there are two free surfaces in the bubble. Actually, there is air inside as well as outside the bubble. So there are two free surfaces in the bubble, and therefore the surface tension will be twice. So it would be 2T into the circumference, which is 2 pi r. So cancelling pi with pi, r with r, p axis will be equal to 4T by r. This is the value of excess pressure inside the soap bubble. Now if we talk about the excess pressure inside the drop, so this is a drop, and drop has only one free surface. This is only one free surface. Okay, so we can say that the surface tension inside in a drop will be only T. So the axis pressure in the case of a drop, water drop, P axis will be 2T by R. Okay, and if we talk about a soap bubble inside a water, this is a soap bubble or water bubble inside water. So this is bubble. So there is only one free surface because the air is present only inside this bubble. So the excess pressure in this case will also be 2T by R. Okay, so these are the probable values of excess pressure for bubble and drop. And in the next video we are going to discuss some more cases on excess pressure. Thank you.